Hello everybody, in this lecture we will be solving 1988 IMO problem number 4. Here's a view of this problem. We would like to show that the set of real numbers x which satisfy the following inequality is a union of disjoint intervals, and the sum of those intervals have a total length of 1988. So first of all, I would like to generalize this result and rather focus on the following expression instead. So f of x is simply equal to 1 over x minus 1 plus 2 over x minus 2 and so on, n over x minus n. Obviously what I did here is I replaced the 70 with n, so in our problem we need to change the n with a 70, and the what I want to show is that this function is greater than, or instead of 5 over 4 I will make it greater than or equal to c. Obviously the function is undefined for x is equal to 1. F is undefined for x equals 1, 2 all the way to n, but pretty much everywhere else it is well defined. So as a result I would define my function on intervals such as k plus 1. So on such intervals for k equals from 1 all the way to n minus 1, I need to add two more intervals, the beginning interval for minus infinity to 1 and the ending interval for n to infinity. Pretty much we have all these n minus 1 interval of the first type and two more intervals involving the negative and positive infinity. So now I observe that our function f is defined on all these intervals, and moreover within each individual interval our function is a decreasing function. It's continuous and it is decreasing. So let's have a look at for example, for any given interval, let's say the generic interval k plus 1. So let me open some space here. So if you consider the value of our function on the interval k plus 1, so let this be the x-axis, and so this is the value k and k plus 1 here, and it turns out that our function, obviously our function is not defined at k and k plus 1, right? So we established that f is not defined for integer values. However, as our function approaches k from the right, like in a calculus sense, what will happen? So we can just focus our attention on the following portion of our function. So our function plus k over x minus k plus k plus 1 over x minus k plus 1 and so on. So these are the two terms that I need to really pay attention to. So as x approaches k from the right side, this guy is positive and this is positive. So because we are investigating for positive values of k, as a result our function will start from positive infinity and it will cross the x-axis and it will go to negative infinity. How do I know it? Because as x approaches k plus 1 from the left hand side, this guy on the second fraction will be negative, but it will be also very close to 0. And again, this side is, the numerator is positive, so as a result we will get a negative infinity here, which will dominate all the other terms, which are just finite numbers. Recall that as k approaches from the right side to, as x approaches from the right side to k, this guy came out as positive infinity, and as x approaches k plus 1 from the left side, this term dominates and it becomes negative infinity, and all the other terms are finite. But then the function will make these shapes, right, like the tangent function, if you will. So let me go ahead and probably try to sketch roughly what I have in mind. So we have our function x, so we have our vertical asymptotes starting from 1 all the way to 2, 3, and so on, all the way to n minus 2, and finally n minus 1. So these are these points 1, 2, and so on, 3, n minus 2, and finally here n minus 1. And our functions look like basically this. So we established that they would look like that, like the tangent function, if you will. Now what we want is we want to figure out for what values of x will our function be greater than c. So let's say that c is, if this is the y-axis here, so this is the y-axis, so c is, let's say here, c. So if you determine the level c, oh, by the way, I forgot to mention what happens before 1, right? So before 1, so when x is less than 1, all these denominators of our function will be negative, and as a result, so our function will be totally negative. So it is still decreasing, obviously, but it is probably, oops, this is the x-axis, so it will probably do something like this. It will have an asymptote at 1, obviously, and the same thing will apply for when n is greater than so when x is greater than n minus 1. When x is greater than n minus 1, actually no, our intervals should stop at n minus 1 here and just n here. Sorry for that. So that's another typo, sorry for that. So as it approaches n from the positive side, from the right side, so this guy will be positive, and this is obviously positive. As a result, we will get a plus infinity, so we will again start at infinity, and as x increases, this fraction eventually will approach 0, right? So it will be something like that. It will asymptotically approaches to 0. So what I'm trying to say, so going back to my story, we would like to find out for which values of x our function will be greater than or equal to c, but you can see it exactly here what will happen, right? So let me identify those points very carefully. So we find the intersection point, we mark the x-axis, we find the intersection point between the c, level c. So we want our function to be greater than these, right? So I will just take care of it now. So the way I will do it is, if for instance, let me highlight it with the green color. So we want to be on this interval here, then this interval here, and so on, this interval, and finally this interval. So we want to add the lengths of all these highlighted intervals in the second step of the problem, right? So before I proceed though, let me just add a little bit more notation. So if you call obviously for these intervals, so we have in total 1, 2, n minus 1, in total n separate intervals will intersect with the y equals c. So as a result, we would have n different solutions, which each solution, let me call it as a lambda k, that would be equal to c for k equals 1, 2, all the way to n. Oops, sorry for that, n. But that's it. So now we know exactly each of our intervals like we described in the highlighted regions here. So all we need to now do is to add these highlighted regions and find out the sum is equal to 1988 if we can. Now for this computation, consider, let me write that down, consider the polynomial q of x, which we defined as follows: x minus 1, x minus 2, and so on, x minus n. It's an nth degree polynomial, and for k in the interval 1 through n, I would like to define let p sub k of x to be simply equal to the polynomial q of x divided by x minus k. So I'm basically just removing the terms x minus k from each one, and I get a new polynomial p sub k. So now we can define capital F of x as equal to q of x times c minus f of x. Now this is a very special construction for a good reason, but let me first expand and calculate this quickly. So this is c times q of x, and when I multiply q of x with f of x, I get that minus q of x times f of x. But let's replace f of x with its original expression now. 2 over x minus 2 and so on, n over x minus n, and that is simply giving rise to the following form. So recall how we defined the functions p sub k of x. So q of x divided by x minus 1 will give us p sub 1 of x minus 2 times p sub 2 of x and so on, minus all the way to I should say minus, I guess, minus n times p sub n of x. So we know that each of the numbers lambda 1 all the way to lambda n are the roots. Recall how we defined those intersection points here on the graph. So these are the roots. So this is where lambda 1 is, lambda 2 is somewhere here, and so on. So you get the idea. So lambda 1 through lambda n are the roots of f of x equals c, as I just showed it here. And as a result, so this would imply that, so this also implies that f of x is also equal to 0 for these values for all lambda k, right? Why? Because look at how we define capital F. So if the lambdas are making this equal to 0, then regardless of what q of x is, 0 times something is just 0. So that those are also the zeros of f of x. But notice that f of x has degree n, right? So that's crucial. So recall that the function q of x has degree n, obviously, and so you have n terms here, so it has degree n. So this guy has degree n, and each one of these has degree n minus 1. So therefore f of x has degree n, and we already have a list of n numbers, basically, for k equals from 1 all the way to n numbers which make this guy equal to 0, suggesting that lambda sub k's are all the zeros that the function capital F has. Now I will try to apply Vieta formulas. So let's try to figure out the coefficient of the term x to the n and x to the n minus 1 in the polynomial f of x. The coefficient of x to the n in q of x is just a 1, so multiply it with c, you get a c here. Finally, for each of these terms, none of them has an x to the n in it. Each one is an n minus first degree polynomial, so that would be the coefficient of x to the n in the function in the polynomial f of x. Similarly, the coefficient of x to the n minus 1 in the polynomial f of x would simply be equal to, so you can the way I will do it is, again, so we have c times the coefficient of x to the n minus 1 in q of x. If you just focus on this expression, it would be just minus 1 times all the x's, minus 2 times all the remaining x's, and so on. So that basically it is just minus 1 minus 2 all the way to minus n. And then the coefficient of x to the n minus 1 in each of these remaining terms is just 1, but there's the coefficients 1, 2 all the way to n, so you get a minus 1, minus 2 all the way to minus n. So now, as I said earlier, I can apply Vieta formulas. I know that the roots of our function are lambda 1, lambda 2, all the way to lambda n, and this is simply equal to the so minus the coefficient in front of this term, which is this long expression, divided by c. So minus in fact, if you will, I can combine these two results. So I would have c plus 1, so c plus 1 times, and then I have a bunch of 1 plus all the way to n, all divided by, so this whole expression, all divided by c, and this is the coefficient of x to the n, so by Vieta formulas for the sum of roots. But then I can, sorry for that. I can further simplify this expression, obviously, right? Because I know the sum here is, actually, let me just move it here. So this, guys, is equal to, you basically have c plus 1 over c. Oh, sorry for that. I no longer have the minus sign either, right? Because I've made all of these positive, and then I grouped them. I factored out the sum 1 plus 2 plus all the way to n. So yeah, there's no more minus sign remaining, and this guy is simply written as n times n plus 1 over 2. And if you look at each of the intervals that I have just showed you, for instance, the first green interval is simply lambda 1 minus 1. The second green interval is lambda 2 minus 2, and so on. That's the sum that I need. So I need to find lambda 1 minus 1 plus lambda 2 minus 2 all the way to lambda n minus n. And that thing is, I can split it, so it is just lambda 1 all the way to lambda n minus 1 plus n, and well, the sum of the lambdas we just established is equal to c plus 1 over c, n times n plus 1 over 2. Let me just close this, minus, again, this guy is n times n plus 1 over 2, sorry for that. Finally, combining these last result, I get that that will give me, so we have an n times n plus 1 over 2 common, and then so let's write that down, n times n plus 1 over 2, and what's remaining inside the first one is c plus 1 over c, and inside the second one is a minus 1 here, so minus c, so you will just remaining 1 over c here, so it's just equal to n times n plus 1 over 2c. Now we can just substitute n is equal to, I believe it was 70, and c is equal to 5 over 4 in this expression, and the result follows immediately, that we get 70 times 71 all divided by 2 times 5 over 4, and that should give you 1988 as we wanted. So that solves the problem. Hope to see you in our next video.